Okay, welcome back guys to our bonding and molecular structure unit. We have finally moved away from C.3.4, which was a long and arduous journey on learning chemistry grammar. Today we're going to be doing a fab lab. C.3.5 means that we are going to be using laboratory observations and data to compare and contrast ionic, covalent, network, metallic, polar, and nonpolar substances with respect to constituent particles, strengths of bonds, melting and boiling points, and conductivity. We're going to provide examples of each type. I know that's a mouthful, seems like a lot, but don't worry guys. I have excellent notes that you will be guided through as we move over into the laboratory setting. But first let's go over our guided notes section, and then you will be performing your fab lab. So there are many different types of substances. Remember that we have ionic bonds which occur when an electron is transferred. This is the negative, full negative charge, and this is the full positive charge, obviously because it's a larger atom. We have polar covalent bonds where electrons are shared unequally. Because the electron cloud is shared, we only can have partial negatives and partial positives. Remember, the partial positive is where the electron is less likely to be on, where the partial negative is where the electron is more likely to be on that side. So it's really about hanging in here rather than hanging in here, but it's in the middle, okay? And it's just a slight variance. Now, pure nonpolar covalent bonds occur in diatomic elements where electrons are shared equally. So here we have two elements of the same kind. The electron dispersal cloud is even, and there's no real charge, okay? Now, ionic metallic bonds occur when metals are bonded to metals. So you have a long strip of metal, and what happens basically is these negative charges of electrons jump around. That is why metal conducts electricity. It's why we use wires when we plug in our laptops or lamps or any kind of wiring system really that we have, whether you're playing on a game or how you get your lights on in your house. It all has to do with this ionic metallic bond, and basically, as I said, it allows for the flow of the electrons to move around easily. It's kind of, they often refer to it as a sea of electrons, they being more qualified chemists than me, of course, the people who named this stuff, probably American Chemical Society or Royal Chemical Society. They decided to call it a sea of electrons. So we also have covalent network macromolecules. Now, one thing that you need to know about a macro molecule, macro means to be seen without eye assistance, basically. So it's something that you can visually perceive. Do macromolecules exist? Yes. The table that you were sitting at is technically a macromolecule. It's a polymer, but you can see what it is, right? So also those will be things that are like crystals. So salt crystals are macromolecules. They are ionic compounds, which are salts, and they are organized in a very rigid fashion. Do you see how this is rotating? And you can see that it has a very definite shape. You can see the cube-like structure as it rotates. That's to indicate that it's fixed in rigid position, and it forms a network of atoms. So it's a covalent network macromolecule. I'm sorry, this is not specific to ionic structures. This is only for covalent bonding. So partial positives, partial negatives, or neutral. Now we have electrons, which are the glue of matter. I'm sure all of you have probably seen one of these at some point in your life or in physics class, but I thought it was a really good way of representing an electron because they are the glue, as it says, of matter, and you really need to think about them as being the active part of the molecule, or a atomic bond, or an ionic bond. This is where all the action happens. It's where it's the sticky stuff of matter. Okay, here we have ionic constituent particles. So we have a bond type, and we have ionics, which are made of ions. So the polarity is obviously, it's very polar. It's polar because there's a full-on positive and a full-on negative. So there are different types of constituent particles. We can have a positive and a negative metallic ionic bond. This, the origin is, of course, the cation and anion benefit here to become closer to a neutral. Okay? So the reason that it occurs is because you have a cation and an anion, and they benefit by becoming closer so that they can be close to neutral as possible. Okay? Positive and negative metallic ion bonds are metals which are bound together. They can quickly change between positive and negative ion states because metals freely give and receive electrons in nature. This explains ductility and malleability. Ductility is basically the ability to stretch, and malleability is form. So, and ductility is also the movement of the electron. So it's conducting something. Conduct. Okay, to conduct means it is happening. Okay, so ductility is the movement of the electrons, which give it its electrical properties, and malleability is its ability to stretch and move and be formed. That's why metals can be easily recycled and used. Positive metal ions and negative nonmetal ions occur when a metal atom, which is broken away from a larger compound by donating an electron or electrons, is combined with nonmetal atoms which carry extra electrons that were picked up in a previous reaction. A positive polyatomic ion and negative nonmetal ion. This means that a polyatomic group had broken away from a larger compound by donating its electrons. Remember, donating makes it positive. And then we have a negative nonmetal ion. Well, the nonmetal atom with extra electrons from a previous reaction. So that becomes an ion. It's an atom which had become an ion by receiving extra electrons. Now we have a positive metal ion plus a negative polyatomic ion. Well, these are metal ions that leave a bigger compound by donating electrons, and they combine with polyatomic groups which broke away from the bigger compound and kept extra electrons. We have positive polyatomic ions plus negative polyatomic ions. This is when a polyatomic group, which broke away from a larger compound by donating electrons, is added with a polyatomic group, which broke away from a bigger compound and kept extra electrons. So one is donating. Donating is positive, receiving is negative. Okay, that's what I want you to remember here. Now we have covalent constituent particles. Covalents are made of molecules. We have the polarity. Some are polar, some are nonpolar. And we have the origin of the constituents. How are they formed? Well, we have nonmetals plus a nonmetal or metalloid. That's all you need to remember. Okay? So we have polar. Remember, polar covalents have partial positives and partial negatives. Nonpolar have no charges at all. So, for a visual perception of a compound is seen without assistance. Macromolecular is seen without assistance. Micromolecular is seen under a microscope. And particulate are models of structures used in experimental methods. Are used to identify. So these are things that you were drawing on paper, which have been identified through experimental methods that came before you. So some of those molecular structures that we've been drawing, that has been theoretically tested and proven. And also computer-based models are examples of particulate structures, things that we cannot visually see. Although they are macro, although they are macro to our eyes, we had to draw them. When they actually exist, they are particulate. They are not able to be seen with our eyes, not even by use of a microscope. So macromolecular particles are unevenly shared electrons between atoms. Covalent network solid states are for experimental analysis. These are macromolecular. Anytime we have a covalent network solid state for experimental analysis, that is something that we can see without eye assistance. Okay? If it's a polar molecule. Unevenly shared electrons between atoms must be in liquid state for experimental analysis. So for micromolecular, it must be in a liquid state for experimental analysis. For particulate, it must be, or it can be, in a liquid, solid, or gaseous state for experimental analysis. A lot of this is because, like I said, we're going to be doing computer models or something that we've drawn. And remember, all of the polar are they're partial positives and partial negatives when we're dealing with covalent compounds. So we have water here, which is polar, and we have the nonpolar, which can be any kind of diatomic element. Again, we're going to be observing covalent network solids for macromolecular liquid states, for micromolecular, and liquid solids and gases for particulate when using models. Okay, this is a new concept. We have strengths of bonds. We're going to be sorting the covalent compounds, the pure nonpolar covalent compounds, the polar covalent compounds, and the ionic compounds. Okay, so with these bond strengths, we have electronegativity differences. Now, what that means is the greater the number with electronegativity difference is the stronger, really, the bond. So we have pure nonpolar covalent bonds, or electrons are shared equally. On a scale of 0 to 4, they're at about a 0.4. Okay, that's about their strength. For polar covalent bonds, electrons are shared unequally. And remember, even though the electron cloud is shared, okay, they're shared. These are shared. Covalent bonds are shared, ionic or transferred, okay? Even though this electron cloud is shared, we have a partial negative and a partial positive. They're shared unequally, whereas nonpolar is shared equally. Polar covalent compounds end up right about here at a 2.0, okay? And then with our ionic bonds, they can range from 2 to 4, okay? So pure covalent range from 0 to 0.4. Polar covalent range from 0.4 to 2.0. Ionics from 2.0 to 4.0. So the basic principle of this for the electronegativity difference is ionics the strongest when comparing with polar covalent and pure non-polar covalent, okay? So strongest, medium, least. Least to most strong, okay? So with melting and boiling points, ionic substances have high melting and boiling points due to their stronger bond force. Let's look back here. Stronger bond force, high melting and boiling points. Covalent substances have low melting and boiling points due to weaker bond forces. Weaker bond forces, lower melting and boiling points. Stronger melting and boiling points. That's a trend, okay? Okay, with conductivity, ionic substances create ions which are great conductors. Metallic ions are the best conductors. That's why we use them. Copper wiring, all these sorts of things that you see in like refrigerators or appliances or other types of appliances or cell phones. They're using metals, and it's because they conduct the best as far as electron transfer. So they are They can also exist as melted ions of other fashions or free ions in water, which are the next best conductors. So you can actually conduct electricity if you have ions that are floating around in water. This is an example of what a battery is like on the inside. You have atoms of the conductor, okay? So what happens is this is the negative end. What does that mean? Well, that means that this has the most electrons, right? And this is the positive end, so that has the least amount of electrons. So in order to balance itself out, what's happening here is these electrons are jumping over. As the energy travels through here, okay, going towards the negative end, what's happening is it's pushing back these electrons, right? They're being transferred. That's what causes the energy to function in a battery. Energy is electron movement, okay? Covalent substances, poor electrical conduction in all physical states. Okay, so if something is covalently bound, it's not going to conduct electricity well. That's why plastics are used for insulators, foams, things like that. They do not conduct electricity well. Rubber does not conduct electricity well. It's a polymer. It's covalently bonded together. Solubility. What is needed to break these substances apart in liquids? Well, ionic substances break apart in water. They are polar liquids. Water is polar liquids, and ionic substances are completely polar. They have full-on charges. So they will, of course, like dissolves like. I want you to remember that. Like dissolves like. Like dissolves like. So if there is a polar liquid, which is water, an ionic substance will break apart. Remember that we learned that sodium chloride, which is table salt, is an ionic substance. If you were to put table salt into water and you were to stir it up long enough, it would break apart. You would not be able to see it. It would disassociate. Covalent substances, they break apart in nonpolar liquids. Nonpolar liquids include lipids. Lipids are a class of molecules that you will learn about in your biology courses. Lipids include oils and fats, okay? This is only one example of nonpolar liquids. There are other many types of nonpolar liquids that do not include lipids. Okay, so in summary, ionic compounds are solids unless melted at extremely high temperatures. They are made of ions. They have high melting and boiling points. They conduct electricity when disassociated in water. Metals are ionic conductors. They break apart in polar liquids. Water is an example. Covalent compounds include gases, liquids, or solids as molecules. They have low melting and boiling points. Covalent compounds are poor electrical conductors, such as solids, liquids, or gases. They break apart in nonpolar liquids. Oils and heated fats are examples of nonpolar liquids. Okay, it's Fab Lab Day. We are going to go ahead and start our laboratory, and I hope you enjoy.